Hello friends, today's topic is MWay search tree. So I am going to give an overview of the MWay search tree along with the properties an MWay search tree should satisfy and the overview, a brief overview of the MWay search tree. So the definition of the MWay search tree can be given in this manner, which I have written already on the board. You can see this and you can take a note of this as well. But I am going to just explain it point by point. What is an MWay search tree? An MWay search tree T may be an empty tree. If T is non-empty, it satisfies the following properties. What does it mean? MWay search tree, that is any tree which is empty, that is nothing is there on the tree. We can see if we see nothing in the tree, we can consider that to be that empty tree to be an MWay search tree. So in that, if the MWay search tree contains some nodes, if the MWay search tree is non-empty, then it should satisfy the following properties, which I have given in a point-wise manner, and I will explain it one by one. So for some integer m, first point says that for some integer m called the order of the tree, each node has a maximum degree of m, or it has m child nodes. The definition is a little bit of technical definition. You need to understand this properly. For some integer m called the order of the tree, each node has a maximum degree of m, or it has m child nodes. A node may be represented as A0, K1, A1, K2, A2, Km-1, Am-1 in this way. So I'll just go on to read it further. So I'm going to explain this part. For some integer m, if there is a small integer, if there's an integer m which is called the order of the tree. What is called the order of the tree? Suppose I say 3. So m is equal to 3. So 3 means the order of the tree. So 3 is that integer which can be considered to be m, and that is the order of the tree. And for that order of the tree, each node has a maximum degree of m. That is, each node of the MWay search tree has a maximum degree of m, or it can lead to 3 child nodes for m is equal to 3, or if m is equal to 5, it can lead to 5 child nodes. So if m is the order of the tree, that means nothing but that means that each node of the MWay search tree will lead to m child nodes. So m child nodes, that is any m which has a value of 3, any MWay search tree which has a value of the order as 3 can lead to at most 3 child nodes. So a node may be represented as, any node can be represented as, how it is represented? A0, K1, A1, K2, A2, Km-1, Am-1. So what is that? Any node can be represented as A0, K1, A1, K2, A2, Km-1, Am-1. What does that mean? That is, we see that there are how many paths which lead to the child nodes? There are m child nodes which can be reached from each node. So that m child nodes can be like this. You can consider this. The m child nodes is starting from 0 to m-1. So 0 to m-1, A0, A1, A2, A3, A4, in such a way it will reach up to am-1. That will lead to lead us to get m child nodes from the particular node. And this K1, K2, Km-1 means we are getting how many m-1 key values or keys, which are the values on each of the nodes of the MWay search tree. Like if I just simplify a little bit with the help of a pictorial representation, it can look like this. Suppose I am just drawing a particular node like this. So this is the A0, A1, A2, and having a having m is equal to 3. So if m is equal to 3, a maximum child nodes which we can reach is 3. So it can be, it starts from A0, A1, A2. A2 is the m minus 1th node. So in this case, if we see that there are two values over here, the values can be like this, K1 and K2. So I have written in this manner, that is, this is K1, this is K2, this is A0, this is A1, this is A2. So there can be 3 ways we can reach the different child nodes to a maximum extent, and there can be two key values in K1 and K2 for m is equal to 3, that is the degree, if the degree is 3. So I have written in that manner. It is a bit of technical writing. So you can just imagine these to be similar to this situation. This pictorial representation will help you a little bit. So I have written for some integer m called the order of the tree. Each node has a maximum degree of m, or it has m child nodes. M child nodes means A0 to A2, and a node may be represented as, a node may be represented as A0, K1, A1, K2, A2 and so on, where Ki means the key values. Ki means the key values starts from K1 to Km minus 1. Say this, K1 to Km minus 1 means m minus 1 is 2 and K1 is K1, and this K2 means Km minus 1. So we are getting these two values, two key values for this particular node which is a part of the binary m-way search tree, which has a degree of 3. So, and in this way, in this part I have written that see this, and AI are the keys, and AI 0 less than or equal to I less than or equal to m minus 1 are the pointers to subtrees of T. So this A0, A1, A2 has been referred to over here. That is, the AI starts from A0 goes to AM minus 1 to a maximum extent. So this A0, A1, A2 means AM minus 1. So all the AI values are starting from A0 and goes to AM minus 1. So there are, in case of this m is equal to 3 situation, there can be a maximum of 3 pointers leading to the 3 child nodes of this particular node which I have drawn over here. So this is the part 1. Number 2 point is that if a node has k child nodes, k less than or equal to m, you can easily understand k less than or equal to m. So if a node has k child nodes, then the node can have only k minus 1 keys. That is, if a node has k child nodes, suppose this node, you can just imagine this situation and compare it to this simplified representation of a node given on the board. So you can see that if a node has k child nodes, suppose this node has k child nodes. How many child nodes? K child nodes. K child nodes means 1, 2, 3. So child nodes which can be reached to a maximum extent is 3. So k is equal to 3, and in that situation we can have only k minus 1 keys, that is k1, k2, k minus 1, that is k1, k2, and k minus 1 over here is nothing but k is 3, so k minus 1 is definitely 2. So we will get up to we will start from k1 and go to k2, and we will get only 3 minus 2, that is 2 key values, that is k minus 1 key values. So this is the point which has been explained with the help of this simplified representation of a node of an m-way search tree. So number 3 point states, for a node A0, k1 a1 dot km minus 1 am minus 1, all key values in the subtree pointed to by ai are less than ki plus 1, and all key values in the subtree pointed to by am minus 1 are greater than km minus 1. That is, we are seeing the key value. Suppose this key value, suppose this has 2 pointers. This K1 has 2 pointers, that is A0 and A1. This is the left pointer, this is the right pointer. For K2, this right pointer for K1 becomes the left pointer and it has a right pointer as well in the form of A2. So, if we go to another node, suppose if we go to another node like this, if we write like this, suppose these are 2 values, 7, 10. So, there are 3 addresses like this, like building blocks in a house. So, you have one pointer like this, you have one pointer like this, you have one pointer like this. So, it will lead to some other node which can have this sort of situation as well. This can also have this sort of situation as well, this sort of situation as well. So, it will have 3 pointers for themselves. They will have 3 pointer for themselves like this one. So, in this way, if we just go to extend this node to one level up to one more level, so we can see that this is one key value which is K1, this is K2, this is A0. This A0 means the address of this node. So, address of the node will be here. The address of this node will be given over here. The address of this node will be given over here. So, this 7 has 2 pointers, one left pointer which goes to this node and one right pointer which goes to this node. One left pointer of 10 is this one which goes to this node and one right pointer which goes to this node. So, it can have values like this. Suppose what we have written is can be summed up by means of an example, some sample values in order to make you understand. That is something which is leading to the left pointer, that is 7 is leading to this address. So, this address, this can contain all the values over here should be less than 7. All the values of this node, all the key values rather of this node can be only less than 7. That is, I am writing about say 2 and 5. So, see 2 and 5 are both less than 7. So, it is on the left part, and the tree is partitioned in this way. This is the method of partitioning which has been referred to in this number 3 point, which I am showing you with the help of an example situation or putting some sample values, because it is a bit of a tricky definition, a tricky technical definition which can be understood in this way. So, this 7 will have a right pointer in this one. So, it will have some values which will definitely be less than which will be definitely more than 7, but definitely less than 10, because 10's left pointer is nothing but the right pointer of 7. So, right pointer of 7 will have some value which is more than 7, which will contain all the values which are more than 7. Suppose I am going to give it a little bit more values so as to cater more values over here. So, if you just take it to be 16. So, excuse me, I have just changed the 10 to 16. So, if it is 16, so its 16's less values will be over here and more than 7 values will be found over here. That is, I can write here 9, I can write here 12. So, this 9 and 12 are all can be seen that 7, 9 and 12 are both more than 7 and 9 and 12 are both less than 16. Similarly, we can extend this concept to this node as well. Suppose this node will always have greater than 16. The values which will be over here should always be greater than 16, because 16 has a right pointer in this node to this node which leads to this node, and this node will contain values which will be greater than this 16. So, that is written over here, and all key values in the subtree pointed to by am minus 1 are greater than km minus 1. So, am minus 1 is this one and km minus 1 is this one. So, km minus 1 values should be greater than km minus 1, that is more than 16, that is greater than 16, and the pointer is leading from am minus 1, and which will all have values, and this node will have values more than km minus 1. Over here this km minus 1 is nothing but k2, and that the value is 16. We can see from this figure, and we can put some figure to satisfy the conditions like this. We can take, suppose I am taking 20 and 25. So this 20 and 25 are definitely more than 16. So this is the way the M-way search tree is being partitioned, and this entire thing which has been written over written in the point 3, I have explained it in the way of this example by putting some sample values in it, so as to make you understand this little bit tricky portion of the entire properties section of the M-way search tree. Now we go to the final point, that is the number 4 point, which says that each of the subtrees AI where I is falling between 0 and m minus 1, that is 0 less than or equal to I less than or equal to m minus 1, are also M-way search trees. That means that the definition which we have been studying so far is a recursive definition. That is, the definition extends to each of the nodes of the M-way search tree. So this is a node of an M-way search tree. So starting from here, we will see that the condition of the M-way search tree holds with respect to this node, and we will also expect that for this node, the properties of all the properties of the M-way search tree should hold. For this node, the properties, all the properties, these 4 properties which have been written over point wise, they will hold for this node as well, and these all 4 properties will hold for the last node of this particular example will hold good. These properties will hold good for this node as well. So we can see that in number 4 is nothing but the recursive way of defining the M-way search tree. That is, each node of the M-way search tree, if the tree is to be an M-way search tree, so each of the node of the M-way search tree will have to be an M-way search tree for themselves. So if each of the nodes of the M-way search tree comprising an M-way search tree are themselves M-way search trees, that is nothing but the M-way search tree defined in a recursive manner. So this is the entire definition and the properties of the M-way search tree. A brief overview, you can say. A little bit of explanation has been given over here with the means of a very small example over here. You can just get a brief idea of how the M-way search tree looks and what it covers, what properties it satisfies, what property needs to be satisfied in case of M-way search tree, and we will carry on with our discussion of M-way search tree in our later videos, where we will perform some operations on this M-way search tree. We will take a bigger example in that situation and go on to insert some nodes stepwise, or we have to delete also. For deletion operations, we will delete some values sequentially from an M-way search tree and see how the addition and deletion properties goes on in a sequential way. So in this video, we are dealing with this much, and we are now keeping that addition and deletion portion for the later videos. So if you have any doubts and queries regarding this entire explanation which I have given to you, you can well post your doubts and queries into the comment section below, so that I can address those comments. Thanks for watching this video.